My name is Rob, and I'm building a hypercar. And today we're starting the design and build of our own wind tunnel. A few months ago there was an enormous buzz on YouTube and other platforms about desktop wind tunnels. Desktop engineering give you a little bit of an idea on how it works, but they're not really scientific tools. What we want to do, building our own Le Mans hypercar, we need a little bit more than that. When we looked online if we could find any plans or hopefully anything open source for building our own wind tunnel, we found two relatively good designs. The first design we found is by a Spanish university, Universidad Europa. That design is really good. They've had great results with it, and they're even working with Airbus, the airplane manufacturer, to do some testing in their design. It meets all of our criteria, except for one. Really two. It uses way too much power, more than we have here, and the design would fit in our workspace, but it would fill it completely up. We couldn't do anything else. The second design we found, and this one is really open source, is from the Live Nebulous project. It's great. It's got the right size, it's got the right power use, it's got everything we need. Mostly. It was designed for fog water collectors. Not really something that we're doing. So in the end, not quite usable for our design to create the optimal race car body. More recently, a portable wind tunnel came for sale here locally. And I'd say, hey, awesome, let's go get that. It's built in a 40-foot shipping container, so it's very portable. And while we would have the space outside, we also like to park our car somewhere, and I don't think our neighbors would appreciate an old rusty shipping container sitting outside. It was built for testing wind turbines, and so it doesn't have the tooling and the measuring equipment we need for our design. So again, not quite what we're looking for, plus that 40-foot rusty shipping container, it's not a great look. So after all that studying, we decided to build our own. Our first design was a blow-through design, and it's sitting right here. Also, this was really the one we built. It features an intake, a fan section, an alignment chamber, a test chamber, and an exit, which I lost somewhere in moving here. It works. It works actually very well. It's powered by 4 sequential, so right one after the other, PC fans, 120 meter square fans. Nothing fancy, harvested them from an old server I had laying around, and actually works fairly well. We did some initial testing with them, so actually I hooked it up. Let's turn it on. And while the design performs well, you just saw that with the paper. Obviously the windows are out, so that's why it's getting a little bit of turbulence. With the windows in, it's perfectly laminar. The paper strips are perfectly straight. As sensors, we use these off-the-shelf, really cheap scales. And the results were just not consistent enough to measure down pressure. They actually work fairly well, but it was not good enough for the kind of performance and the kind of details we want to get. So the way we did that, there's holes in the bottom of the test chamber, and we would just put pins in and have the model sit on the pins. So that way you can measure the pressure, the downforce as the wind goes across the model. And that works fine, because this actually works very well, and you may want to build this at home. We'll make sure the plans are online after this project finishes. And we're showing actually the CAD files on the screen right now to give you a little bit of idea how it's actually built up, because it's kind of hard to see with the 3D printed model I have here. As you've already figured out, this is not our final design. While this works, it's not quite up to the standards that we like to achieve. So we kept designing. And finally we got to design number 3. And that's what we're going to be building. And while the one we just showed you was powered by these PC fans, the one we're actually going to be building in this series is powered by this. It's a recirculating design, similar to the one from Universidad Europa, with a large 1x1 meter fan housing, with a sweeping 180-degree turn up, guiding the air from the fan housing to the test section. The test section is made up of 3 main elements. An alignment section with circular tube with a length of 400 millimeters, followed by a test section with a cross section of 400 millimeter wide by 300 millimeter tall, over a length of 1000 millimeters. At the end, there's a debris shield, just in case something goes wrong. The test section protrudes into an exhaust section that features another 180-degree turn back into the fan housing, recycling the air. The exhaust section or diffuser expands in cross-section and volume rapidly to reduce airspeed and pressure. There's a small air gap from the outside of the test section to the exhaust fan, And that allows any overpressure to bleed off quickly or any underpressure to suck in additional air. And this keeps the system balanced with the environment. So our test chamber is 400 millimeter wide, 300 millimeter tall, and 1000 millimeter long. That's small, too small for any full-size parts. But our 1 in 10 scale, like we showed you in the previous video, model can fit in there easily. So we can easily test parts that are 1 to 10 scale and then scale up for the calculations. And our wind tunnel is powered by this 2.2 kilowatt fan, 400 volts, 3-phase, that pushes just over 24,000 cubic meters of air per hour. That is just north of 14,000 CFM, a lot. And we will be controlling that motor with a variable frequency drive that can run up to 5.5 kilowatts. Why the 5.5 kilowatts, you may ask? We've got the small motor and the big VFD. Well, very simply, 2 reasons. This way we can grow, maybe put an even bigger fan in the future, but maybe more importantly, we were able to get one for a very good price on the used market. And you know, budget is important. In the fan housing, we'll be building several over and under pressure valves. Just in case something goes wrong or we did our calculations wrong, the pressure has a way to get out quickly and doesn't cause any catastrophic failures. Because it's a fully closed system, the air circulates in the wind tunnel while it's running. We effectively have a 2.2 kilowatt heater going in a very small space. It's about 2.5 cubic meters of air with a 2.2 kilowatt heater. Well, that's like having your clothes closet with a space heater. It will heat up quick. So that will happen in this wind tunnel. It will heat up very quickly. But temperature and humidity are 2 very important indicators when looking at the aero performance. So it will really skew our results. So to counter the effects of heating because of the fan running, we're adding a cooling system. So there'll be a radiator of some sort in front of the fan to cool the air as it's going through the system. How we're going to do that exactly, I haven't decided yet. We've got a very big fridge sitting here, so maybe we'll just put a vat of water in the fridge and circulate that to a radiator, or maybe we'll get an industrial chiller if we can get one for the right price. In the front part of the test chamber, there will be a slot in the floor, and attached to that slot will be a vacuum. And the reason for that is so we can take out any dirty air that's sticking to the sides of the test chamber, especially to the bottom, the floor of the test chamber. So we get clean air under the car and get optimal performance for a car. Obviously, if we have a part that's in the middle of the test chamber, we wouldn't need that. But this way, we improve the chances of having great laminar flow right on the surface of the bottom of the test chamber. There are going to be 2 mostly separated electrical systems for this system. First, the big one, 400 volts, 3-phase, 6 amps, pretty big, for the fan. The control box for the fan we picked up locally, used, cheap. It was a standby spare for a local factory. Really good price, and it's got everything we need. With its own enclosure, own safety systems, and obviously meeting all the codes that are required for this location. It's also got an emergency stop and a maintenance lockout and everything else you can imagine. That's also where the VFD lives. The second electrical system is for the sensors and controls. And while there's a feedback loop to the main electrical system to turn on the fan, that's really the only feedback loop there is. The low voltage control system is 5 and 24 volts, depending on what sensors we're trying to power. For the controls, we have 2 closed loop systems. The first one, airspeed. How fast does the fan have to go? By turning on the VFD at a certain frequency, that will in turn make the air flow at a certain speed. And that will be balancing itself. Then a second control system will look at temperature. As the temperature rises, the system will turn on the cooler or increase the cooling and so on. Those are the control systems for the main features of the wind tunnel. For our speed sensing, we have a single wind speed sensor to mount in the test chamber, and it's rated for 70 meters per second, so very high speed. The second part of the electronics and the sensors are the sensors for the results, the measurement results we're actually looking for. Obviously, we're using the wind speed and the temperature sensor that are also in the closed loop system. There are also several other weight, deformation, temperature sensors that we use to gather data from the test object. The first test chamber we're building will have a circular cutout in the bottom. So the 400 millimeter wide section will have a circular cutout in there with 4 pads that have weight sensors on them. And they'll be roughly in the places where the wheels of a car would be. Now, obviously, if we test something else, let's say a wing, we would just make sure that they have 4 mounting positions on those 4 pads. Those 4 pads will notice pressure differences individually. So we can see if the car is weighted left front, left right as the air speed changes. So it will give us a good indication of the performance on the back, the front, left and right of how the car works. That whole circular cutout in itself will also have sensors, and that will be on deformation sensors. So it will measure how far it's being pushed back. So how much air pushes against the test object, for example the car, while the air is going. So we can look at how much resistance does the car have from the air that hits the front. Now, why is that a circular cutout? Well, very simply, we want to be able to rotate it. So it won't be automatic, we'll have to manually rotate it, but we can rotate the car so to see what happens when the air hits it from the sides or 10 degrees from the side. What if the yaw pitch is not quite straight on? Maybe you're steering in, you're drifting a little bit, or the wind comes from the side. Just to make sure that the car stays stable at high speeds turning into a turn. And in order to do that, we have that deformation sensor, not just in the direction of the wind flow, but there's also one at 90-degree angle of that. Then when it rotates, we combine the two and we can calculate the wind resistance of a car or whatever test subject we have at an angle. In front of the test platform, there will be a slot so you can insert a smoke generator. So we can introduce a smoke stream that will make the aero visible over the surface of the test subject, the car. And to help us visualize that even better, we'll be introducing a couple of line lasers to give us a perfectly flat, horizontal or vertical view of where the smoke is moving and how it's going through the planes. Behind the test platform, there'll be another slot. And that one will be used to insert a differential air pressure sensor so we can see what the air pressure does in different spots behind the car. To make sure we can track what's going on and keep some control over it, we're adding cameras to the inside of the test chamber. And we may even add a window to make the cameraman happy so we can actually record something instead of just a static display that makes a lot of noise, but we'll see about that. All of this will be controlled from a single web browser-based control interface. So it's easy to control everything, record what's going on, record all the sessions, name them, save them, and use them for later reference. And as always on this channel, we're building the wind tunnel completely in-house. In order to build the intake and exhaust parts, the 120-degree sweeping that go from a square meter to test chamber size, we're using the CNC machine that we're building in the other videos. We're making the inside shape out of foam, putting fiberglass over it so we can have excellent surface finish and dimensional accuracy and build this thing ourselves. More on that in the build videos. And now for the why. Why do we need a wind tunnel? Well, we're building a car. And our plan is, once we build it, it will go fast, really fast. And we want to make sure it's safe and fast and safe in corners and, well, in every other situation we can imagine. And we don't have all the resources that the large car companies have. We don't have a library of prior designs that we can pull from. We have to design everything from scratch. And in order to do that, we want to use a very quick, iterative process. Design today, CNC it tonight, test it tomorrow morning, redesign tomorrow afternoon, and then it starts all over again. CNC at night, test in the morning, and so on. We can do a lot of testing with OpenFOAM or other CFM software. Works great. But nothing beats actually seeing the results in real life. So that's why we're building our own production and test capabilities right here in-house. So what kind of performance do we expect to get out of this wind tunnel? Our own calculations based on this big fan and the spec of that fan from the manufacturing, and our own CFD calculations using OpenFOAM show that we can achieve speeds of up to 67 meters per second. Well, I'm sure not everyone knows what meters per second actually means in real life. It's 240 kilometers or 150 miles per hour. So very, very quick. We can achieve very high performance in this wind tunnel. As always, we're doing this project on a budget, just so it saves us money, but also to give you the opportunity to build this yourself. Maybe our design completely, maybe you improve on it. Hey, that would be great. Let us know, or maybe we can improve our design as well. This is not a cheap project. The fans, the VFD, the materials, they add up. But we sourced a lot of the materials used. The fan is used from a supplier locally and is less than 10% of what a new one would cost. Same for the VFD. And I would urge you to do the same. Adjust the design based on what you can get locally. The way it's looking right now, building the wind tunnel, including all the sensors with a single test chamber, we can keep sub 2,000 euros. And I think that's pretty good for something with this kind of a performance. Now, we're going to build this over the next couple of episodes. It's going to take a couple of weeks to build this, and we'll keep you updated. And at the end, we'll give you an exact budget and tally of what materials we used and what it actually cost. And that's really all there is to say about the design of the wind tunnel. We will be building this over the next couple of weeks, months even, and there'll be several episodes dedicated to this build. So keep watching the channel and you'll learn how to build your own.